Welcome back to The Explainer. Today, we're diving straight into a fascinating behind-the-scenes mystery of a truly iconic product. We're going to uncover the ultimate intersection of engineering and imagination, the Lego brick. Let's explore the sheer scale and accuracy of this manufacturing process together, because honestly, this science behind it is absolutely mind-blowing. Okay, let's dive into this, because there is a core engineering paradox we really need to unpack here. Think about it. How does a brand new brick manufactured today perfectly, and I mean snugly, fit one made decades ago? We're talking about millions of pieces produced every single day, working in flawless harmony with toys created way back in the 1950s. It isn't just a toy, it is an absolute masterclass in mass production. So let's find out exactly how they pull this off.
Section 1. The perfect precision mystery and history.
Section 2. ABS plastic and raw pellets. To really understand this modern marvel, we have to recognize that this brand has been refining this exact process since the late 1950s. The secret to their incredible longevity isn't just a fun idea, it's the relentless pursuit of manufacturing perfection, and that starts right on the factory floor with the raw material. Look, you can't just use any standard cheap plastic for a product that needs to snap together and pull apart thousands of times without degrading. You need a very specific chemical cocktail known as ABS plastic. ABS stands for acrynitrile butadiene styrene. And yeah, it's a mouthful, but each of those three complex words serves a totally critical engineering purpose. The acrynitrile provides chemical resistance and intense hardness. The butadiene is a synthetic rubber that gives the brick its impact strength. Actually, that's exactly why they don't just shatter into a million sharp pieces when you accidentally step on one in the dark. And finally, the styrene gives the brick that iconic, satisfyingly glossy finish. Together, this specific polymer blend gives us what engineers call clutch power. You know that satisfying click you feel? That's clutch power. It's the perfect grip that can hold a massive 3,000-piece spaceship together against gravity, but still allows a child to easily snap it apart with their bare hands. ABS plastic gives the brick its incredible strength and the resilient memory to maintain its exact microscopic shape over decades of rough play. But before they become those iconic blocks we all know, the ABS plastic actually arrives at the factory in the form of tiny, raw granules or pellets. They kind of look like clear, coarse sand. But here's the thing. You can't just melt them down immediately. There is a crucial, often overlooked preparation phase. ABS plastic is highly hygroscopic. In everyday terms, that basically means it naturally acts like a giant sponge, pulling invisible moisture right out of the air. If you were to take these raw, moisture-filled pellets and toss them straight into a superheated melting machine, well, that trapped water would instantly vaporize into steam. That steam creates microscopic bubbles and silver streaks, known in the industry as splay, which completely ruins the structural integrity and the precise dimensions of the final brick. We definitely do not want that. To prevent this, these tiny granules are carefully loaded into massive silos and baked at high temperatures to completely dry them out. Once they're perfectly bone dry, they're mixed with a highly concentrated colorant known as master batch. This is what transforms that clear plastic into those vibrant reds, blues, and yellows we know and love. Now they are the perfectly prepped blank canvas, completely stabilized and ready to be subjected to extreme conditions to take on their final form. Section 3. The injection molding process. All right, this is where the magic happens, and frankly, this is where the engineering gets wonderfully intense. Inside these massive factory machines, it is an endless, rapid-fire heartbeat of production. First, those dried and colored ABS pellets are superheated to roughly 232 degrees Celsius, or about 450 degrees Fahrenheit. At this exact temperature, the plastic melts down to the consistency of warm honey. Second, this molten liquid is injected into highly complex, customized molds. But get this, it's not just poured in, it is forced in under immense pressure. We're talking about machines applying anywhere from 25 to 150 tons of clamping force just to keep the two halves of the metal mold tightly shut while the plastic fills every single microscopic crevice. If that pressure drops even slightly, the plastic leaks out the edges, creating a flaw called flash. Third, once the mold is perfectly filled, a network of internal cooling channels pumps cold water around the metal, rapidly dropping the temperature. This locks the plastic into its exact mathematical shape in literally a matter of seconds. And fourth, the molds open, and the fully solid bricks are automatically ejected into a collection bin right beneath. Melt, inject, cool, auto-eject. A complete cycle takes around 7 to 10 seconds. And the wildest part? These machines run 24 hours a day, 7 days a week, all year long.
Section 4. Robotic laser quality inspection.
Now, just think about this incredible journey for a second. We've gone from messy, raw, unmolded plastic pellets to a mathematically perfect finished brick. But how do we actually guarantee that generational clutch power we talked about? How do we ensure a brick minted today fits a brick from 1982? I mean, human eyes alone couldn't possibly keep up with millions of bricks a day to check for microscopic flaws. Instead, as the bricks travel down the line, highly advanced automated lasers and high-speed robotic cameras scan them. These robotic inspectors check the physical tolerances to a staggering 10 micrometers. To put that into perspective, a standard human hair is about 70 micrometers thick. So these machines are checking if a plastic brick is off by 1/7 of the width of a human hair. No way, right? If the metal mold has worn down over time and a brick is off by even that microscopic margin, the system catches it and it's instantly rejected. The rejected bricks aren't just thrown away, though. They're ground back down into pellets and recycled right back into the melting process. Only the flawless, mathematically perfect pieces actually survive this gauntlet.
Section 5. Printing, Packaging, and Distribution.
So here's the crucial point. While the bricks are now structurally perfect, they aren't exactly ready for the toy store shelf just yet. The logistics of turning bins of identical pieces into specialized sets is its own engineering marvel. The journey wraps up with 3 major, highly automated steps. First, unique pieces get routed to specialized machines for printing. Think of a minifigure's face or an intricate control panel. They use a process called pad printing, which operates with absolute alignment, stamping ink onto a 3-dimensional object with incredible accuracy. Next comes the sorting and packaging, which, honestly, is mind-bending. Giant robotic systems drop specific bricks into bags. But how do they know they didn't miss a single tiny piece in a 1,000-piece set? Well, they use highly sensitive weight scales. A tiny, single 1x1 plate weighs about 0.16 grams. As the bags are filled, the scales weigh them in real time. If a bag is off by even a fraction of a gram, an alarm sounds, and the bag is automatically pulled off the line for a human operator to go in and fix. Finally, these perfectly counted sets are boxed up, loaded onto pallets by autonomous vehicles, and seamlessly enter a massive global distribution network bound for stores worldwide.
Section 6. Mind-blowing manufacturing facts.
Before we look at the final numbers here, I want you to actively think about this. Let's zoom way out to the macro scale. Given everything we just discussed, the careful drying of the pellets, the melting at 450 degrees, the precise injection molding under 100 tons of pressure, the rapid cooling, and those relentless 10-micrometer laser inspections, take a guess in your head. Try to do the mental math. How many Lego bricks do you think are produced every single second across their global factories?
Okay, ready for it? The answer scales up to over 100 million elements produced every single day. When you break that staggering daily volume down, it translates to well over 1,000 pieces manufactured every single second. By the time I finish this sentence, thousands of perfect laser-inspected bricks have just been born. This completely shifts our perspective, doesn't it? It is one thing to engineer a single perfect brick. That's a great piece of design. But it is an entirely different level of genius to engineer a global manufacturing system that can repeat that exact process over 1,000 times a second, 24 hours a day, without ever sacrificing that microscopic clutch power. It's an absolute triumph of mass production and quality control working in perfect harmony. You know, there's a great saying for this. Every product has a story. It's so easy to take everyday items for granted, right? We buy a box, we rip open the plastic bags, we snap the pieces together, and we just expect them to work perfectly every single time. But beneath the surface of the most common, unassuming products in our lives are massive, hidden worlds of brilliant engineering, precise polymer chemistry, and cutting-edge robotics. The things we consider simple are so often the most complex. So let's see how this builds your curiosity moving forward. If a simple plastic toy requires this much innovation, thermodynamics, and precision, imagine the secrets hiding inside the rest of the objects sitting on your desk right now. If you love discovering the hidden processes behind everyday products, you are exactly where you need to be. Which amazing product's hidden process should we unpack and explore next? Let us know in the comments, keep that curiosity alive, and I'll see you in the next explainer.